Okay, should I start?
Good morning, everybody. Welcome to our weekly machine learning seminar. Today, we'll have a pleasure to have a talk from Dr. Philippe Baratta from Aix-Marseille University, France, Europe, Earth, Solar System, Milky Way Galaxy, who will be talking about statistical methods in observational cosmology. Philippe, the virtual floor is yours. Please go ahead.
Thanks, Jacob, for this introduction. So indeed, today I would like to present you some data analysis aspects of modern cosmology, which is the domain that tries to understand and describe the universe as a whole, and also that tries to understand the evolution actually of the universe and also its structures, its cosmological structures at very large scales embedded in this universe. And also I would like to focus on observational cosmology, which tries to confront two main blocks. First, the measurements, okay? The measurement of some cosmological probes that we measure thanks to telescopes and satellites, etc. And that must be confronted to different cosmological models. There is a multitude of cosmological models that aims at theoretically describing gravity, the evolution of our universe. So this is what we want to do in observational cosmology. In this presentation, I would like to give you an overview of the different steps that we usually use in cosmological analysis. So namely, how we go from a specific observation measurements of some cosmological probes and how we can obtain at the end of the analysis chain this kind of plots representing the constraints on some physical parameters, right? So in this example here, I picked the measurements of the cosmic microwave background, or CMB, which is basically the very first light emitted by the universe about 400,000 years after the Big Bang, that we can still observe today. It has been measured by Kobe in 1992, then WMAP, and finally by the Planck satellite that can provide us this tiny fluctuation in this radiation, in this light, that can be translated into fluctuation in temperature, because there is, as you may know, a direct relation between temperature and radiation. And we got this very tiny fluctuation of temperature of about 10 to the minus 5. So we obtain this anisotropical structure that we want at some point to compare to the different prediction of the different cosmological models that wants to be tested. And this is very ambiguous to obtain data, because we don't know how to directly compare this kind of map with our predictions, our theoretical predictions. And to do that in a proper way, in a clean way, one can do these confrontations at the level of some statistical quantities that we can both estimate on this kind of map and that we can also predict from cosmological models. For example, we can estimate from this map the angular pore spectrum of this fluctuation of temperature in the CMB. I'm going to present you in more details the pore spectrum in the next slide. So this is not the subject of this slide. So, okay, we know how to estimate some statistical quantities right from this observation. These are represented in the blue dots here with error bars. And we want to compare with the different theoretical predictions. We pick one cosmological model that we want to test, and then the idea is to find the right parameters, the right cosmological parameters in this model in such a way that the model fits the data. right? This is in a procedure that we call cosmological parameter inference. And the end of the procedure, the final idea is to obtain such a plot, okay? For the CMB analysis here, this is represented by this very elongated ellipse that represent the 1 sigma, 2 sigma, and 3 sigma constraints on these two specific parameters, omega m and omega lambda. Here, omega m represents the total fraction of matter in our universe, about 30%. And here, omega lambda represents the total fraction of another energy components in our universe that we call the cosmological constants, that we think to be related to the acceleration of the expansion of our universe, which is about 70% here. And so I'm not entering details about this physics here, but if you are interested in knowing more about expansion of the universe, etc., maybe we can talk about this at the end of this presentation. And also, we can do this kind of analysis with other cosmological probes, like, for example, supernovae, like that are basically stars at the end of their life that are exploding, which represents a mine of physical information. We can do this also with BAO, that stands for Bayon acoustic oscillation. So basically, this is a statistical study of galaxy distribution in our universe, which is also a information, and which is actually the probe that I'm going to focus on in the next slides. And as you can see, the ellipses are not oriented in the same way. This means that if we do a joint analysis between all of these probes, at the end, we obtain this very sharp constraint on these two specific parameters. But actually, we can do this on multidimensional parameters, and we can, for example, for this analysis, obtain some estimation on these physical parameters that governs the evolution of our universe. Okay, so these are the main steps that we are doing when running a cosmological analysis. Okay, so let's finish with this introduction and let's focus on my specialty, which is a galaxy clustering probe, which is another name to talk about BAO. As I said, this is a statistical study of galaxy distribution in our universe and how we can obtain from this observation some constraint on cosmological parameters and physical quantities, etc. In this field, we usually play with what we call the density fluctuation fields, delta, that can be constructed from the local deviation of the matter density in the universe with respect to the average density in the universe. Okay, this is a three-dimensional field that depends on time and space. Theoretically, we would like to make some prediction on the evolution of these fields through cosmic ages. And to do so, one can resort to the usual continuity, Euler, and Poisson equation, which form a nonlinear system of equation, linking these delta fields to its kinetics through the velocity field. So this provides us both the kinetics and the dynamics of such of the behavior of delta. Also, yeah, here A represents the scale factor of the universe. So basically, its volume that may vary, okay, because our universe today is expanding. And also here, omega m here is, as I said, the total fraction of matter in our universe with respect to other energy components like radiations, like cosmological constants, or like other exotic fluids like dark energy, dark matters, etc. Okay, so if we want to compute a prediction for the behavior of these delta fields, one has to solve this nonlinear system of equation. However, this procedure is highly complex because of these nonlinear terms here in the right-hand sides. And in a fully analytical way, we don't know how to provide a full prediction on the behavior of delta. That's why usually one has to resort to numerical n-body simulations, like this one, the Millennium n-body simulations, which are about several millions of light years of size, where you can see through cosmic ages, structures forming, structures clustering through this time parameter that we call the redshift here. Z equal 0 is today, and the higher is Z, the younger is the universe, and there is a nonlinear relation between the redshift and the usual time. And here, what you can see here are just galaxies accreting to each other to form these very large-scale structures that are also called galaxy clusters or the cosmic web. Okay. Okay, so at this point, we know how to make some numerical predictions on the evolution of some overdensities in the universe. We can follow an overdensity and see how it evolves, how it clusters as time passes. However, at some points, we want to compare these numerical predictions with data. But this is very difficult. This is very ambiguous because with our observations, what we obtain is a fixed picture of the universe today. We don't have access to the evolution of single structures in the universe, right? So it is more practical actually to adopt a statistical description of these density fields in order to compare predictions with observations. What we can do is to construct some functions that are called two-point correlation function psi that can be built from this field theoretically. Okay, we picked this field at two random positions in the universe, R1 and R2, and we do so at all possible positions in the universe. And following some cosmological principles that I'm not going to details here, we end up with a correlation function that only depends on a single parameter, r, which represents the distance, the separation between all of these overdensities in our universe. Actually, we don't know how to make a direct prediction, a direct theoretical prediction for these objects. But this is not the case, fortunately, in Fourier space. Actually, we can do the same exercise. We can construct the same two-point correlation function in Fourier space, and we obtain its equivalent, which is called the pore spectrum. And fortunately, the pore spectrum can be theoretically predicted no matter the cosmological model that we want to test. So here, I wanted to illustrate the shape of the pore spectrum as a function of the Fourier wave modes, following two different recipes. The linear recipe, okay, just following the left-hand side and without accounting from these non-linearities. Okay, we can do it. We can solve this using some numerical Boltzmann codes, and also following the nonlinear prescription, so accounting for these nonlinearities, also using some Boltzmann codes. But at some level, because in the nonlinear regime, at very small scale, the results are not accurate enough to compare directly to data. But still, I just wanted to show you the shape of the pore spectrum. First, you can see that as time passes, the overall amplitude of the pore spectrum is enhanced, okay? Both in the linear regime, the large scales here, which are about several giga light years, and here also the pore spectrum is enhanced as time passes at these small scales. Small scales in cosmology are about millions light years. Everything is relative. Okay, and you can see when comparing the linear and the non-linear prescription here and here, that in the small regime, in a small scales, the pore spectrum is enhanced also. So if we want to probe the small scales of the universe with next generation of galaxy surveys, for example, we have to take into account these non-linear terms, right? So also I wanted to show you that this pore spectrum is also sensitive to some physical quantities, like for example, the mass of neutrinos. If we add some mass to neutrinos, for example, this respectable one, which is the one that we expect actually from data, you can see here the difference in the pore spectrum in the massless and massive neutrino cosmology. And we expect in the next generation of galaxy surveys that we will be able to make a difference between these two curves. So namely, we will be able with cosmological probes to provide constraints on the mass of neutrinos. That's that because today we don't know the right mass of neutrinos, even with particle physics experiments. Okay. So now in these slides, I wanted to show you that the pore spectrum is also sensitive to other physical quantities, other cosmological parameters. The total neutrino mass, as I said, okay. Here a denser color means a larger value for this parameter. So the pore spectrum is sensitive to the mass of neutrino. This is also sensitive to this parameter. This is a very important parameter in cosmology. It represents the expansion rates of the universe today. So this is also sensitive, but in a different manner. It is also sensitive to the total baryon density in the universe, both in the linear and nonlinear regimes. It is also sensitive to other parameters like the physics in the primordial universe that we call primordial inflation that happened right after the Big Bang. Okay, it's also sensitive to the spatial curvature of the universe and also some exotic components like the dark energy that we think to be responsible for the accelerations of the expansion of the universe today, and also the dark matter that we have to add to our equations because structures are too much clustered today. So we have to take into account this exotic fluids and also this one. Okay, so just to tell you that the pore spectrum is sensitive to a lot of cosmological parameters governing the evolution of the universe, but but also the Earth physics like neutrino mass and baryon density and etc. Sometimes we do not know how to estimate. We cannot estimate this three-dimensional pore spectrum because some probes are not defined in 3 dimensions. Like for example, the cosmic microwave background. This is a radiation that we observed around us in 4 pi steradian, and which is defined on the sphere. So in this case, we can also estimate some kind of pore spectrum, which is called the angular pore spectrum, defined on the sphere. And to do so, one has to resort to another basis, which is called the basis of spherical harmonics, the YLM. And in this case, theoretically, if we want to make some predictions on the delta fields, the idea is to project the delta fields on the basics of spherical harmonics. To do so, first one has to erase this radial dependency on the delta field, just to have angular dependency, just using some window function which depend on observational features, observational constraints, etc. And the idea is to expand this field on the basis of the YLMs. And at the end, so I'm just skipping some details which are not really important here. At the end, one can construct the similar of this 2-point correlation function here, but on the basis of spherical harmonics, which are called the angular pore spectrum, or CS, right? And theoretically, one can link the pore spectrum to the angular pore spectrum. This means that if we know how to predict this guy, we also know how to predict this guy. So this is a good news. One can compare the different measurements of the angular pore spectrum, like for example the CMB, directly with our theoretical prediction of the different models that need to be tested, right? So here, this is the very same slide as previously for the pore spectrum, just to tell you that here also the angular pore spectrum is also highly sensitive in its shape to a lot of physical quantities, but in a different manner. Okay, so let's come back, let's close this parenthesis, and let's come back to the main object, which is the three-dimensional pore spectrum. So we know how to predict it at some level using Boltzmann codes. We also know how to estimate it directly from data. So the idea is to take data from galaxy surveys or from n-body simulations, for example, and then to estimate this delta field. Okay, just taking this definition. The local density with respect to the average density. So we construct these delta fields. We perform a Fourier transformation of it in order to obtain delta k. Then we apply this estimator, this very simple estimator in 3 dimensions, and then we obtain the three-dimensional pore spectrum that we can project in 1 dimension in order to compare it with the corresponding prediction. So the data are represented, the fake data here are represented in red here, with error bars that must be accounted and are accounted in what we call a covariance matrix, which is a very primordial object in cosmology. I will come back on covariance matrix because it is very important. It must take into account the instrumental constraints, the instrumental error bars, the theoretical error bars and data correlations. So what are the theoretical error bars here that must be predicted prior to the analysis? This is because we are observing a universe, a stochastic realizations of our universe. And we are in this single stochastic experiments. We are not traveling through different universe. We are only standing in one stochastic realization of our universe. And at some points, we must provide some theoretical error bars related to these facts, right? I will come back on the prediction of this theoretical covariance matrix, which is very important in cosmology and which correspond to a big issue actually today. So let's come back to this. The cosmological analysis, the main idea actually is to play with the different predictions for the pore spectrum to find out the right parameters, cosmological parameters, okay, in such a way that prediction fits the data. Okay, this is quite standard. And to do so, we can do that in a clean way using Bayesian inference, using what we call the Bayes theorem. The Bayes theorem, the idea is to sample a posterior distribution, which represents the probability of a certain set of the probability that a certain set of cosmological of a certain set of cosmological parameters are true, given the measured data and in the framework of a cosmological model that we want to test. The final idea of the analysis is to sample such posterior distribution. In other words, the posterior distribution are these ellipses. The final idea is to draw these constraints on parameter, these ellipses. And to sample this posterior distribution, the idea is to evaluate a likelihood distribution, which is quite standard. The likelihood distribution is a bit different in its interpretation. This is the probability of observing such data given a certain set of chosen cosmological parameters that we are trying to test, also in the framework of the same cosmological model that we are testing. Okay, I will come back on this likelihood distribution, okay, in this second part here. And also in the analysis, one can add some prior knowledge that we want to add to our analysis, as for example, the fact that we are only seeking for neutrino mass that are positive, or maybe we are also we know that some cosmological parameter must be embedded in some interval, in some sharp interval, or in some Gaussian interval, I don't know. Or sometimes we only want to combine this analysis with another past analysis, saying that such a parameter must be in this interval, or we have some knowledge about some parameters, etc. Okay, these represent some prior knowledge that we want to add to our analysis and to influence our posterior distribution. Okay, and also this last term is not really important. This is called the evidence, and it acts only as a normalization of this term here. So let's come back on the likelihood, which is the main object when sampling this posterior distribution. The likelihood model depends on the measured data through a chi-square. Okay, the measured data, the measured pore spectrum, for example, the theoretical pore spectrum that we are testing, the covariance matrix, as I said, but it must correspond to a certain distribution, and usually one has to model this distribution, and the idea is to make the hypothesis that data are Gaussianly distributed. And this can be discussed actually, but usually this is what we make in cosmology. The hypothesis that data, the pore spectrum, is Gaussianly distributed. So the idea is to model this. So we model this as a multivariate Gaussian distribution that depends on the covariance matrix and on a chi-square. Okay, that depends on data, on the prediction, etc. So if we want to sample the posterior, the idea is to find out every chi-square when we are varying the set of cosmological parameters in our analysis, right? So, and the idea is to minimize this chi-square to find out the best fits of our cosmological model. So now let's make a little parenthesis on the covariance matrix. As I said, the covariance matrix has some contribution, the contribution of the instrumental errors, but also the theoretical errors. So let's talk in more details about the theoretical errors that must be accounted in such analysis. So the idea is to predict the covariance matrix, the theoretical covariance matrix for the pore spectrum. The standard definition of the covariance matrix is this one. If we develop theoretically this term, this expression here, we end up with this expression here that can be split it in two contributions. The Gaussian contribution, which is actually the easy part because it only depends on the amplitude of the power spectrum, but we have this power spectrum. But that's why this is very easy to predict this term. However, and unfortunately, this is not the case for this second contribution, what that is called the non-Gaussian contribution, because it depends on this term, which is defined as this double integral on this term, which is called the tree spectrum, which is constructed as the 4-point correlation function. Okay, this is not the 2-point correlation function, this is the 4-point correlation function that we need to predict if we want to predict the theoretical covariance matrix that will be exploited in cosmological analysis. However, if we try to compute theoretically this guy, we end up by dealing with these two guys, and actually they are dominant in the computation of this tree spectrum here. In other words, we don't know today how to predict this second term, which is highly important in our cosmological analysis. You may say that, okay, we don't know how to analytically predict this term, but maybe one can simulate it using, once again, numerical simulation, numerical n-body simulation. This is right. One can simulate several n-body simulations, estimate on each of them the corresponding pore spectrum, apply this estimator to obtain a certain estimate of the theoretical matrix. Right, we can do this for analysis. However, for the next generation of galaxy surveys, in order to reach a certain level of accuracy in the results of our analysis, we will need to provide a covariance, a non-noised covariance matrix. And this can be quantified that we will need to provide about 5,000 n-body simulations in order to obtain this unnoised covariance matrix that can be exploitable by the next generation of galaxy surveys. However, our today numerical infrastructures can only obtain one n-body simulation per day. So in other words, this is totally impossible to reach this number of n-body simulations. Okay, we can actually reach 50, 100 n-body simulations that can be exploitable. However, the corresponding estimated covariance matrix is too noisy to be used to be exploited in a realistic analysis. That's why here this is one of the biggest challenge of today cosmological analysis. We don't know how to provide an accurate theoretical covariance matrix, which is fundamental. That's why there is a whole area of observational cosmology where we are trying with statisticians, with data scientists, etc., that are trying to simulate in a faster way these catalogs of galaxies in order to obtain these good estimates of the covariance matrix that will be exploited in cosmological analysis, right? You're following me? So there are lots of possibilities to generate in fast way, but equally accurate way, these catalogs. This is actually my specialty. I've made my own method that allows to generate in fast way some Monte Carlo catalogs that allows to bypass the gravitational evolution that is usually done in n-body simulations. I'm not going to enter in details. I don't think I have time. I don't think I have time at all. So I will skip this slides and just pass to this slide. Okay. So just for you to know that the covariance matrix is a very big challenge today in modern cosmology because we don't know how to provide to the cosmological analysis a right covariance matrix, an accurate covariance matrix. Once again, due to this term, the tree spectrum. Okay, so let's come back to the Bayesian inference. Let's say that we have an accurate covariance matrix to be exploited in such analysis. So the idea, once again, is to sample this posterior distribution. How can we sample this posterior distribution and at the end obtain such ellipses, such constraints on parameters? So the idea is to explore the whole parameter space that is multidimensional. Maybe we are testing sometimes 10, 15 cosmological parameters. This means that for each set of cosmological parameters, one has to reevaluate the chi-square through the likelihood. So to reevaluate a prediction for the pore spectrum. However, each prediction for the theoretical prediction takes roughly 1 second. So this means that this is very, very long, and we cannot explore a whole multidimensional parameter space with this time. That's why there is several solutions to bypass this issue. First, some cosmologists are using machine learning approaches to fasten the process of pore spectrum prediction based on the outputs of Boltzmann codes and also n-body simulations, etc. This is not my specialty, so I'm not at all. I cannot speak in depth about this thing. But there is another choice that is used today in cosmological analysis, is to only sample a certain part of the parameter space using an optimal choice of sampling, which is called MCMC, for Monte Carlo Markov chain, which is a widely used algorithm to explore the parameter space. It allows smartly to only explore parameter space where the chi-square is small, okay? Where the parameters, the cosmological parameters, are likely to represent our universe. So we do that several times, several thousands of times, and it will, with some convergence criteria, it will sample this posterior distribution, the 1 sigma, 2 sigma, 3 sigma, etc. And to do so, the idea is to first find out the minimum of the chi-square that we call the best fit. This is the best set of parameters that allows to represent the data. And with some specific delta chi-square, one can draw the 1 sigma, 2 sigma, 3 sigma confidence interval, and then to draw this very clean ellipses that we obtain at the end of such analysis, like this plot here. Okay, this is my last slide. So to conclude, observational cosmology is now a data science that has to deal with big data, both from the side of observation, because we have to deal with billions and billions of data, and also from the side of theory, because as I said, for example, for the theoretical covariance matrix that we have to provide, this must be obtained from thousands and thousands of numerical simulations, from n-body simulations, Monte Carlo simulations, etc. So that's why cosmologists observational cosmologists are also data scientists. We are using usually we are using Bayesian inference for such analysis. but we have a lot of issues. We have a lot of challenges, like for example, as I mentioned, the covariance matrix prediction that we have to provide. It's very difficult to provide an accurate and precise covariance matrix due to all of these things that I just said. There is another problem that I didn't mention, is likelihood modeling. As I said, we are using a Gaussian multivariate distribution. So we are making the hypothesis that data are Gaussianly distributed, but maybe due to there's nonlinearity, this is not the case. This is something that we have to address. And that may lead also to some biases in the final results of our analysis. And another problem that I didn't really mention also is the fact that when we are using Boltzmann codes to make some prediction on the matter pore spectrum, actually in the nonlinear regime, as I said actually previously, in the nonlinear regime, the results are not really accurate, because if we compare this prediction with the output of n-body simulations, actually, which are our reference, n-body simulation are our reference. Actually, there is some discrepancy, some deviation of about 5–10% in these nonlinear regimes. However, the next generations of galaxy surveys will exploit these nonlinear, these very small scales. So we have another issues here is the fact that we don't know how to make accurate prediction of the matter pore spectrum in the nonlinear regime. So all of these things may bias our final analysis, and this is a big issue. Well, this was my last slide. Thank you for listening. If you have any questions or comments, I would be very happy to have your feedback. Thank you.
Thank you, Philippe. So I'm opening the discussion. Whoever wants to ask question, just switch on your mic or camera and ask question. I have 1 or 2 questions from my side. Okay, so maybe I will. Okay, I can see Stefan. Oh, Stefan.
Hello, Jakub.
Yeah, hello, Stefan. Go ahead.
Oh, sorry, I didn't know if it was unmuted or muted. Sorry about that. Thank you, Philippe. That was super nice talk, very inspiring for people who know not much about it. I see Gwenda is in the audience, and she's probably the one who knows the most around here. And on my side, I have a lot of questions, but I cannot ask everything, so I'll make a selection. First of all, I'd like to ask you if you are working in space or in space-time, and whether or not that has an influence on the type of statistics that you're using, because I guess if you are on some sort of non-flat space, which maybe some people could call that manifold or something like that, would that pose certain difficulties statistically, or is that completely irrelevant to what you're doing?
Is a question, are we observing, are we comparing prediction with observations at a given time without accounting for the depths of the universe with the light cone? It's the fact that when we are looking far away, we are looking in the primordial universe, etc. Is that the question?
I mean, basically, I'm asking if you're using some sort of relativity in your in the observations, or if everything is.
Sure.
Yeah.
Exactly. Yes, because well, the pore spectrum that we are using here can be predicted actually at a given redshift, at a given time. Okay, and this is a problem, because we are looking every time actually in our observations. We are looking at different redshifts. I don't remember if I mentioned it, but the redshift is the time. Yes, I mentioned it. Redshift is our time parameter here. Z = 0 is today. Z = 1 is several million years before, etc. So actually, the idea from observation is to slice our observation between different redshifts. We take a single redshift, we estimate on it the pore spectrum, and we do so for several redshifts, from, for example, for redshift 0 up to redshift 1. And then the idea is to run an analysis that compare these measured pore spectrum at different redshifts with our prediction of the pore spectrum also at different redshifts. So this is a joint analysis taking into account this depth in our observation. And yes, we are at some point using relativity, because in the prediction of the pore spectrum, we are using relativity. Am I answering your question?
Yeah, definitely. And then a sub question of this, thank you, is that when you're doing this, the statistics that you are doing with the correlation matrices and the Bayesian inference and so on, you are basically, I think statisticians call this spatial statistics, in a sense that you are, for example, if you're looking on the Earth is not Euclidean space, it's a sphere, more or less. So the way to relate 2 points on the sphere statistically is different from the way you would relate 2 points on a plane somehow. That's what I understand from my colleague statisticians, and I cannot explain it very well because I'm not able to, write the equations down myself. But I'm asking myself the question whether the fact that you are working in some sort of space-time continuum has an impact on the types of statistics that you use for your description of the system that you're looking at.
Okay, I have two answers for that. First are we probing some geometry of the universe, if the universe is spatially flat, or if the universe is spatially a sphere or not, etc. Yes, this is exactly what we are doing in such analysis, because as I said, the pore spectrum depends on this omega k parameter, which is the spatial curvature of the universe, which is a parameter that directly enters the equation of general relativity. So yes, through the pore spectrum, but not only, with other cosmological probes, we can probe, we can know if the universe is flat or with different other geometries, right? I have another answer if the question concerns our statistical probes that we are observing. The pore spectrum here is defined in 3 spatial dimensions, on which one can add the time dimension. As I said in my previous answer, we can estimate the pore spectrum at different cosmic time without any problem, and compare to the corresponding prediction also at different cosmic time. Okay. Sometimes we don't have access to these 3-dimensional dimensions, 3-dimensional spatial dimensions. Sometimes we don't have enough accuracy on the depths of the object that we're observing. Like for example, the redshift. We don't have information on the redshift, but we only have the angular information on all of the objects that we are observing. And in that case, we can change the basis of our observation. We can work on the sphere, okay, on the sphere, which is also the case for this probe, the cosmic microwave background, which is actually a radiation that we can measure all around us. And for a radiation, there is no depth. We can only see it, let's say, on the sphere. And in that case, we can also apply on such measurements some statistical quantity estimators, which are the 2-point correlation function, but on the sphere. So yes, we are working on different space. Here, the basis of spherical harmonics, or in Fourier space, etc., depending on the kind of measurements that we got. Am I answering your question or not?
Yeah. You definitely are. Thank you so much. That was very helpful. And maybe I can ask another one, because then I'll have to disconnect, unfortunately, for another meeting exactly at 11. So maybe I can steal a bit of time. It will be very short. So when you are doing these estimates when you say you're doing Markov chain Monte Carlo, and you are trying to estimate the areas in which the quantity that you're interested in varies very much with respect to the parameters, and which areas in parameter space they do not vary very much with respect to the parameters. Are you able to use some sort of derivative Monte Carlo approach, or some other version of this, maybe multi-level or similar, that would allow you to, for example, by looking at the derivative of the quantity that you're interested in with respect to the parameters, focus the parameter space where the evaluation of that function, the quantity of interest, is most useful to your predictions? Is that something that you do in your work?
Okay, I think I understand the question. Is the fact that in our posterior sampling, the fact to obtain the 1 sigma, 2 sigma, etc., are we using some derivatives of our observable that we are using, like the pore spectrum, etc.? Actually, if this is a question, actually, we are doing that for forecasts, actually, without any data analysis. For example, and this is what we call the Fisher analysis, Fisher forecasts. Actually, this is what we do before launching a satellite, or before building a telescope. Actually, given our instrumental constraints, given our covariance matrix that we will use in our analysis, and given the statistics that we are using to compare the data and the predictions, we can obtain such kind of ellipses, doing some derivatives that are embedded in the Fisher formalism. But this is only for forecasts. When we are using data, we are not using such kind of method. We are just using standard Monte Carlo Markov chain algorithm with different metropolis hastings. I don't remember the other kind of algorithm that are embedded in such MCMCs, but at the end the result is the same, and we obtain the same contour plots. The only difference is that we can converge to the end quickly or not. But well, we are using standard Monte Carlo Markov chain at the end, just using our data, our predictions, our covariance matrix, given a likelihood model. This is all that we are doing. We are exploring, thanks to this very smart algorithm, our parameter space that allows to find out the right region in parameter space where cosmological parameters that we are testing are the best to represent the physics of our universe.
Very clear. Thank you so much. And I have I have many other questions, but I won't ask them. Thank you so much for the presentation.
Thank you for your questions.
And thank you, Jakob.
Thanks, Stefan, for asking questions. Sure. So any other questions from the audience? I have maybe one. If we could go back to the slide, I think it was slide 3 or 4, where you had this plot of the data in the log scale.
One?
No, number further?
Spectrum, this one?
No, where do you have this plot with uncertainties later, maybe?
This one?
This one, yes, on the top
Okay.
right. So what I can see here that you have quite high uncertainty of the data at the large length scales, right? So this is the short wave numbers, right? This
Exactly.
is the
Large scales.
small, large scales, right? And here we have a small uncertainty of the model, right?
On the model, yes.
Yeah,
actually, well, please go on.
And it is the opposite on the other side of the powers of the wavelengths, right? So for the
exactly.
Yeah. So how to understand this from the? I mean, first it gives you some combined high uncertainty of your modeling approach, perhaps, right? Because you have either high model uncertainty or high data uncertainty that you need to deal with.
Yeah.
So is it something that bothers people, or maybe it is something that's
actually this is yes, this can be predicted. Such error bars that are larger at large scales than at small scales can be predicted. This is what we call the cosmic variances. The cosmic variance, which is related to the fact that we are living in a single stochastic realization of our universe with a single realization of the pore spectrum. But if using n-body simulations, I simulate different universe with different initial conditions, I will end up with different pore spectra. Okay, in average, I will find out the pore spectra that is made by my cosmological model, if the cosmological model is the right one. However, since this represents some stochastic realization, I should have such error bars, which are theoretical, that are not related to instrumental errors. Actually, the instrumental errors are very, very small with respect to the theoretical errors. And why this error bars is larger at large scales than at small scales? This is mainly because we are working in Fourier space. In Fourier space, the idea is the procedure is the following. We start from a galaxy catalog measured or obtained from n-body simulations. Okay, the idea is to sample on a grid our delta field, our contrast density field, and then we apply on it a Fourier transform. Okay, so we have a delta K grid, three-dimensional grid, and then the idea is to project this three-dimensional pore spectrum here in one dimension. This means that if I am focusing on small Ks, so large scales, I will only okay. Let's see this in this kind of a box. Let's see this in 2 dimensions in this box. I will have a grid, okay, a 2-dimensional grid, and if I'm focusing on shell averaging, this is what we call shell averaging, the procedure of going from 3 dimensions to 1 dimensions. I will average modes that are here, but I don't have a lot of these modes at large scales, which is not the case at small scales, where I will average on these shells where much more modes will fall in this shell. So the error bars is directly linked to the number of independent Fourier modes that I am averaging when doing this projection procedure. That's why at large scales, error bars are larger than at small scales.
I see. And it is completely not related to the fact that these correlations that you have in your system that you're observing are not present in the same time, meaning that what we observe in the faraway galaxy is present in the much earlier time, and the galaxy far away, when observing us even in the earlier in time, right? Because
no, this is not related to the fact that because we take into account the fact that for a galaxy very far away from us, the pore spectrum at that time is different. We are taking this into account. This is only related to these two facts: the fact that we are standing in a stochastic realization of the universe, and the fact that we are using Fourier space actually.
I see.
Okay. But if we did the same analysis in 3 dimensions, the 3-dimensional pore spectrum and the 3-dimensional measured pore spectrum and predicted pore spectrum, which is actually not possible, the error bars would be smaller. But we can do this.
All right. Thank you so much, Philippe. I think we should finalize the session today because it is 11:03 now. So thank you very much for your very clear and nice presentation. It is, I think, very much related to the machine learning and data analysis that we are focused at here. And it was an interesting topic and application that you provided to us. So thank you so much for doing so.
And thank you so much, everyone, for listening.
And thank you, everybody for your attention. And I will keep you posted about the future seminars. So have a good day.
Thank you. Bye. Bye, everyone.